Okay, so my name is 2L, and I've been asked to give an overview about numerical relativity. How, as Trudy said, you have to consider that the audience doesn't know much about relativity, numerical relativity. You have to be as elementary as possible. And usually these are the types of talks I hate most, because it's really difficult to be technical, and it's very difficult to be technical and exhaustive. So I've done my best, but please do interrupt me if I sometimes get too technical or I don't give you the right thing. Anyway, the reason why I accepted it is because I think this idea of trying to join different communities interested in the same topic is a very valuable one, and I think Pau is doing an excellent job in this respect. So here's what we try to talk to you about. First of all, I'll try to explain why we do that. Okay? And then I'll try to tell you why it is so hard. The title says there have been 12 great months, and I'll try to give you my personal highlight of the last 12 months and how we feel we made huge steps forward. I will tell you also something about the progress in numerical relativity ADEI, both in the recent past and in the more on a longer time scale, and then what is our future work and conclusions. So, what is it that numerical relativity wants to do? Well, first of all, it's very ambitious. Okay? If you are not ambitious, you don't start numerical relativity. We want to solve Einstein's equation without approximation, but we don't like approximations. We want to do things example. Of course, we don't always do that. Most of the time, we have to do some kind of approximation. But at least in principle, that's the idea. So, Einstein's equation without approximation. One of the problems in relativity, which is unsolved because it doesn't have any solution, is the binary problem. And this is one of the aims of the method. So, study what is the equational motion of a binary system which is interacting over the gravitation. Then we use gravitational collapse. This is another of those solutions of Einstein's equation, but also physical puzzle, the most common, that has a lot of complexity and needs to be investigated numerically. And of course, there is the problem of what happens when you have gravitational collapse, when you produce horizons, you have a length, you have and so on. Numerical relativity also allows you to study stars which are so compact that cannot be studied perturbatively, especially when they undergo nonlinear evolution for instability. And of course, then produce templates for gravitational wave detection. Now, this is not just an academic exercise. We are academics, but this is not just an academic exercise. And in order to commit you, I think you already know that there is several million euros and 1,000 man hours which have been spent in these apparatus trying to develop, build them, and detect data. And of course, at least here on Earth, knowing the waveforms, matching them with filters, can compensate a very small signal-to-noise filter. And this will allow for detection in the first place, but also make source characterization possible. By the time that these detectors will work and in the advanced stage, we will get signals. We will want to understand what are these signals, how can they tell us something about physics that we don't know, and this is called source characterization. And it is possible just if you know in advance what is the source properties of producing a certain waveform. So, why is it so hard? Well, let's start from the fact that mathematically it's a covariant theory, right? That means you can write answer the question in tensor form, but that's it. You don't have no idea what you can write on best which form of writing. Historically, the ADM decomposition is being used, but for formal decomposition of the same equation is unclear whether it's better to write them as a first order in time, second order in space, first order in time, first order in space, second order in time, second order in space. What doesn't really know? Can you hear me? I usually shall. So, first of all, we don't know how to write equations. And of course, that's a beauty mathematically, but it's a pain if you want to solve the equations. Then coordinates, both space and time, do not have a specific meaning. This is a freedom, a gauge freedom, but as any freedom, it has to be handled with care, because you do the wrong choice and you don't get the right answer, or not the answer you really would like to have. Just to give you an idea,
suppose that you want to cover a certain portion of your space-time, okay? For those of you who are familiar, this is just a way of summarizing both space and time. This is a Penrose diagram, okay? This is a black hole space-time. So you have here spatial infinity. Here's the origin. Here is Xi, plus and minus. Well, there are many different ways in which you can cover this. Suppose that you want to cover this with your with a set of coordinates. You can think of using space-like slices, in which case your outer boundary is at a finite distance. Okay? This is a standard way in which, for instance, fluid dynamics works. Okay? If you want to study a problem, you just say, my problem is over this length scale. I cover this length scale over with a certain number of coordinates, and I study it. So here you have spatial slices which have finite extents. The problem is that most of the time when you do this, the outer boundary is in a place where you don't know the solution a priori, and that makes use of boundary condition very complicated. So most of the time, having a finite extent outer boundary gives you headaches when you try to give boundary conditions. And headaches that can be so severe that your whole solution will die because of this. Well, then you can say, well, so what? Then just put your outer boundary at infinity. See, here I'm covering up to infinity. This is my spatial infinity. At any time, I cover spatial infinity. So this is a way of doing things which is neat because, you know, remove the problem of spatial and of outer boundaries. But on the other hand, this is a problem because you have to cover sufficiently all wavelengths when they move from your region of interest down to infinity. And that is complicated numerically. You start having reflections and all sorts of under-resolved regions on your domain, which you then have to solve in other ways. Then you have an even different approach. What are the degrees of freedom? Well, the degrees of freedom move at the speed of light. So, and particularly if you're interested in studying gravitational waves, then the most natural way of doing this is by using a null foliation. See, here my coordinates just follow light rates, okay? And this is another way in which I can do things, but while it is mathematically very well defined, it's much less intuitive, and getting from here to physical variables is complicated, not to mention the fact of getting initial data and so on. So you see that even where to put your coordinates is problematic in numerical relativity. And what we usually do, and most people do, not everybody, but most people do, is to have something like this. There are people like Franz Pretorius who is doing something like this, or not quite like this, but an intermediate solution between these two. But the standard choice is to have outer boundaries at finite extents. So then gauge conditions. You have this freedom of putting coordinates where you want them, and most of the time these coordinates have to be dynamically adjusted. If something happens in a portion of your grid, which is bad for your calculations, you want to make sure that things happen there with your coordinates so that you don't suffer from it. A simple example is singularities. Okay, suppose that you have the following problem. You have something which is collapsing to produce a black hole. Here is the black hole horizon, and this is your space-time. Okay, so in principle, you want to calculate the solution at any point in this plane. You are here with as an observer. You want to get gravitational waves. Then you can use the simplest slicing, we call this, the simplest way of setting coordinates in time, and these are just parallel space-like hypersurfaces with constant coordinate time. Well, if you do this, it's called geodesic slicing. Then you see, you start here, everything is fine, but then at one point there is a singularity. Once you hit that singularity, there's going to be a portion of your code which is having divergent fields, which you cannot resolve. Then at this time, t20, in these coordinates, the code will crash. You are here, you're waiting for your waves, and you will never see them. Okay? This is a typical example of how not to do things. The kind of exercise you ask your student to do the first time they learn about numerical relativity. So the way you solve this problem or go around it is that you shape your foliation. Okay? You let time, because it's just a coordinate after all, and relativity is nothing but saying how to lay coordinates. You say, well, time will go slowly over here and will go fast over here, so that you will have the solution in this time and you will detect your gravitational waves. On the other hand, in the inner parts, there where the solution will hit the singularities, nothing really happens. And one example of this singularity avoiding slicing is the maximal slicing. So you see that there are ways in which you can play your cards properly, but it's important that you do that. Also, another problem is grid stretching. If you have portions of your space-time where the fields are very intense, then the coordinates will fall, for instance, if, just like because of the potential, gravitational potential. Or if you have something which is in rotation, there's going to be frame dragging, and everything will be dragged. And so if you have a certain coordinate system which is regular, and you place into a space-time which has a dragging, all of your coordinates will start to be tangled, and you don't want that to happen. Otherwise, you will not be able to use your techniques, which are usually finite difference. So gauge conditions have to be used, which counteract, for instance, grid stretching. Then, well, just look at the equations. The equations are highly nonlinear. There are claims that this is the most difficult set of equations to be solved in physics. And what is worse is that we don't really understand or know the properties of these equations in these nonlinear regimes. What we can get from our colleagues mathematicians are theorems of well-posedness, which are very important, but it's just, not enough for us. Saying or knowing that a certain formulation is well-posed, that is, that it will at most grow with exponential errors or exponential instability is not enough. Anything which grows exponentially will be completely useless for us. We need something much better definition of what is a good idea and what is a bad idea, but it's something that is not possible to get from a mathematician yet. And of course, physical singularities, well, these are butter and bread of numeric relativity. We study most of the time things which are very compact and which tend to become black holes, or you start already from black holes. So you want to be able to get around the problem of singularities. A very common idea is that of excision, okay? So, again, you imagine this is a slice, space-like slice, and inside, in the black area, there is a singularity. What you do is, you know there is a singularity because there is an horizon, an apparent horizon, which is found on this slice. Well, you just cut out a portion of that domain, and you don't solve the equations there. Relativity tells you that you are inside an horizon, so you are in a causally disconnected region of your space-time. Whatever happens in the yellow or in the black region should not matter for the blue region. All the light cones are tilted, we say. Well, this is in principle. In practice, what you do is, most of the time, most of us use codes which have Cartesian coordinates. The horizons have spherical topology, so you cut out something which is a sphere in Cartesian coordinates. What we call this a Lego sphere, from the Lego, the Lego toy. Okay, so it's not a perfect sphere. You have edges and corners, and these usually are sources of problems because the equations there are extremely nonlinear. It's sufficient that round-off errors can be produced there and then propagate outwards, despite the fact you are in a causally disconnected region. Okay, so all sorts of numerical problems are possible, and we see them. In addition, when you want to do this, you have to find the apparent horizon. That's an expensive operation. And most of the time, if you have a black hole which is excised, and this has to move and orbit, well, so you have to move this excised region. So this is an additional bookkeeping operation, which most of the time is not trivial. Actually, we have people who have been working on this for months now. And then you simply have more equations to solve. This is stretching supercomputers' resources. This is not a minor issue. You have huge turnaround times to make this makes experimentation difficult. I'll show you some results, and these took 2 to 3 weeks. You just wait 3 weeks to know whether your choice was a good one or not. And clearly, the kind of progress you can do is very slow. And other technical issues, AMR, adaptive mesh refinement. Well, this is not a trivial issue, especially in relativity, because you have nonlinearity, and this comes up, especially at boundary. So, what is it that we do most of the time? This is our set of equations. Okay, so Hans's equation, no approximation. Sometimes you have the right-hand side here being 0 if there is in vacuum, but we also like non-vacuum configuration. So in that case, we also need to have equations, other dynamic equations, so conservation of energy and momentum, conservation of baryon number, and equation of state. This represents to us our approximation to reality. Okay? All of this can be improved. And it's, you know, it's a layering process in which every time you know how to do something, you try to do to improve it and put some more physics, maybe into the equational state, magnetic fields, putting viscous terms, radiation transport. This is, you know, our timeline for the next 10 years. Now, I thought it would be a good idea to give you a simple how-to do numerical relativity, so that after this, over the coffee break, you can go and build your numerical relativity code. But I'll just try to give you essentially what is it that most of us uses most of the time. So we tend to, you know, relativity says coordinates are just coordinates. Time and space are just the same, but we tend to neglect this idea, and instead we say space is not equal to time, and we select a time coordinate and a space coordinate, and so we slice things in this 3+1 decomposition. 3 because you have 3 spatial dimensions, and then you have 1, which is the time. So these are these surfaces sigma t, and over you write your line element in 4 dimensions in this way. So you can really split the presence of a trimetric, which tells you how to measure things on each of these light blue slices. And then there is a shift vector, which tells you how a certain coordinate on one coordinate slice is reflected onto the next one. And then there is the lapse function, which is telling you just how the time changing, how 2 clocks on these 2 slices have different ticking rates. That's how we do most of the time. And of course, alpha, the lapse, and beta, the shift, represent our gauge conditions. Okay, a choice for alpha is a slicing choice. A choice for beta is a choice for the shift, for instance, to compensate for the formation of the grid. So because you have this hypersurface sigma, you can think that this is embedded in a 4-dimensional space-time. Then you can measure what is its curvature. This is called extrinsic curvature. It's a tensor. And essentially tells you, if you take a vector and you move it to neighboring points, what is the difference in the angle between the 2 vectors. Okay? This is proportional to this tensor. So in this formulation, this 3+1 splitting, and in the standard ADM formulation, what happens is that Einstein's equations are written in this way. So this is just a time derivative. It's a Lie derivative, but it's essentially a time derivative. You have the time derivative of the trimetric is proportional to the extrinsic curvature. You can look at this as an equation of motion. dtx is equal to IA, where this is the acceleration. And then here the acceleration, the time derivative of the acceleration is proportional to the curvature. Now, this is really a very simplistic way of looking at these equations. But essentially you have 6 because it is a 2 tensor in a 3-dimensional manifold. It's symmetric, so you have 6 plus 6, 12. First order in time, because these are just time derivative PDEs. Okay? And you involve gamma ij and kij. And what I write here, these are just the matter terms. Okay? These are lengthy expressions which you don't need to pay attention to. This is the kind of equation we evolved, so you really have just 12 equations to evolve. And sometimes some people do calculate also the constraint. So at any time you assume that these equations are satisfied on each slice. This is the equivalent of divergence B equals 0 or divergence E equal 4 pi rho in electromagnetism. They should be satisfied, and once they're satisfied at the beginning, they are satisfied at all times, at least in principle. They never satisfy at the beginning, and they tend to grow as a matter of fact. These are elliptic equations, very different from these, very expensive to calculate. Most of the time, no one calculates. We just calculate in the sense that we don't solve them. We just compute them to see whether the left-hand side is really 0 or not. Okay. Then, of course, because as I said, we do other dynamics. That's one of our focus at AEI. We also need to solve the other dynamic equations. Now, we try to do things in a fancy way, and we write, instead of using the standard form in which we would write the divergence of the stationary tensor, we use flux conservative form. This allows us to use a number of theorems which tell us that we're doing the right thing. And what you do essentially is that instead of using standard variables like the density, the energy, the velocity, you introduce new variables which are called conserved variables, which are these fancy combinations. They don't mean anything in physics, but they allow you to write this divergence in this form. So this is a flux conservative form. you see essentially you have a state vector u. You take its time derivative, and it's proportional to the divergence of these fluxes. Okay, this is very similar to an advection equation, just fancier. Okay, and you, of course, you don't need to know what's inside here. This is not exactly flux conservative because it is not zero, but there are no derivatives in here which include matter variables. So this is essentially our setup. And now I would like to tell you about the 12 great months we've just experienced. It is 12 months because on September 16th, this paper came out. Actually, before I tell you about that paper, let me tell you why there were 12 great months. So a number of difficulties which have hindered progress in numerical relativity have been recently overcome. How do you measure this? Well, just look at the production. There are 7 papers on physical review letters, 7 on physical review D, 2 on classical quantum gravity, and 1 on RPJ letters. These are either been submitted and published, or they are awaiting review. But they are all good pieces of science. Overall, you can say that numerical relativity calculators have never been as accurate and stable as they are now, both in vacuum and non in vacuum. People around the world, and AI in particular, are simulating a number of different sources, from binary black holes, single and binary neutron stars, black hole, neutron star binary systems, and so on. And numerical relativity is, for the first time, starting to provide the data analysis community with some information about the physics of the sources. So far, we tended to move at different rate, the different rhythms, essentially because we were lagging behind, but I think we're catching up fast. So why is it that these have been 12 great months? So I will say, I'll give you some highlights. These are my personal highlights. About the 16th of September 2005, Franz Pretorius surprised essentially the whole community by showing these calculations. Right now, these calculations are not impressive. Actually, now that we've seen this, we see that it's not that accurate, and the waves are not as nice as we can do now. But what it was important is that essentially he did everything in an unconventional manner. He used a different form of the equations. He wasn't doing this 3+1 splitting. He was using a different way of getting the initial data. Rather than having black holes already present, he actually produced black holes by collapsing a scalar field, something very bizarre, if you think, but worked fine for him. The evolution scheme were different from the ones we usually use. He was using implicit and very expensive, and he was using this conformal compactification, which I was mentioning. But the important thing is that he showed that you can have orbital motion in a binary system, something which people were not able to do before, and the first waveforms were extracted. If you are been in the field enough, you know that this looks like this looks like what you would expect. People have looked for this type of waveform for a long time, but never seen it. So it was obvious that this was the right thing to do. Some other highlights. This is a paper actually produced here at AI in collaboration with colleagues at LSU. So these are the most accurate simulations in black holes in the co-rotating gauge. Co-rotating gauge was the standard way of doing things before Franz Pretorius startled people that you really have to move things. What is important in this paper is that it shows you that you're really just having not enough resources to solve this problem, and with the low resources that we have now, you can get easily the wrong answer if you don't do the right choice. So here is the proper distance, so the separation between this binary system of black holes, which is orbiting and whose trajectory is shown here, as a function of time. So clearly the things are merging, and so this curve decays. And you see there are these dotted blue dots. So this is the if you want the exact solution, the end solution. And then there are a number of lines, blue, green, and red. And these are all different realization of the same initial data and the same evolution. And so if you ask it, at a given time, what is the distance between the two holes, you can get very different numbers. And the reason why that happens is because gauges are playing such an important role at this low resolution. If you crank up the resolution, then all the curves tend to converge to the right one. But of course, we don't usually have such high resolution. And this has been a very important lesson to be learned, that if you don't do things right, exactly right, you will have problems getting the answer. Then there was a meeting in November at NASA, and these results were presented. So this is the result from the UTB group. And there they show, once again, now with a set of techniques which is common to the ones I've shown in the previous slide, using punctures. So this is a way of approximating black holes, that these punctures can move. They were allowed to move, while before we were working in this co-rotating gauge. And you see there is an orbit, or about an orbit, and you get something which looks like a waveform. Remember the one from Pertoids? This looks also pretty much similar to that one. So this paper was followed. In fact, if you see they are adjacent in physical review letter, by the work by the NASA group, which was using a different code and different techniques. They were using AMR. And the important thing about this paper is that for the first time there is an indication of what you might call the universality. You have to think, so what the NASA was able to do is to start from larger and larger separation and find out that no matter where you start, at the end you end up with the same trajectory. It is as if you have dug some grooves in your space-time, and if you start with two balls which are farther apart, at the end they will end up in the final grooves. And you can see this in the trajectory, so these are different initial data. And also in the waveforms. These are different waveforms. There are 4 different waveforms, but the final part is always the same, exactly because you are ending up in the same grooves. Now, this is universality, quote-unquote, because as a matter of fact, there are going to be slight differences. But what this result is telling us is that the differences are very small. Some more highlights. Soon after that, the group at Penn State produced the first results on unequal masses. So all of the examples I've given you were coming from equal masses. The two black holes had the same masses. Here they are unequal, and you start seeing something more interesting. So if you look at this waveform, it's kind of obviously boring. I mean, there's this part here. There are these 2 pixels. It's a short number of cycles. So there isn't a lot of excitement. But you see, it's just almost a continuous fit that you would do from post-Newtonian expansions. Here you start seeing that as the mass are not equal, then you have higher multiples, equal 3, 3, 3, 3, 1, 2, 2, which are excited and then produce a signal. This is exactly what you would expect. Again, NASA, now they start measuring kicks. So this is, of course, a very important issue for LISA. And here you see that they get numbers of the order of between 150 and 200 kilometers per second. UTB, again, these guys have clearly an advantage over others. And here there is the first results indicating the spin-orbit coupling. This is a purely relativistic phenomenon. Well, I think it's not purely relativistic. You think you can also have in Newtonian physics. But it appears in this context just in pure relativistic regime, because the context here is that you have aligned spins or anti-aligned spins with the orbital one. You don't see that in Newtonian mechanics. So here you have anti-aligned, so you have the two bodies are going like this, okay? So, and here you see that with respect to having 0 spin, the trajectory is accelerated, the in-spiral is accelerated. And here instead you have the spins which are aligned with angular momentum, and you have that what is called orbital hang-up. Things remain in orbit for a longer time. So this is something which we are still verifying, and it's clearly a very important and interesting physical process. Well, but there were 12 months not only in vacuum simulations, also in matter simulations. This is a paper by Shibata and Shapiro's group, and they were the first to do an axisymmetric collapse of a differentially rotating and magnetized star to a black hole. Here you see these are just density and velocities, and here is the magnetic field. You see that you start from a poloidal magnetic field, and you end up with something which is still poloidal but as a funnel, and this funnel could then be the site for the acceleration of particles or the production of a jet. These simulations are just the first step. There isn't enough energetics to convince that this is the way gamma ray bursts work, but it's a first simulation in full GRMHD. Again, no approximation made, besides the one of being axisymmetric. This is a self-propaganda. This is another important paper, I think, in these 12 months. This is the first time that using a different technique it was possible to study the waveform produced when a black hole is formed from the collapse of a rotating neutron star. In the past, people being us, would be able to stop there where the red line is, and that was the best people could do. Now you can see that the whole waveform is known, and essentially, once you know this, you can say that a 40-year chapter has been closed, and you can start doing physics. Now I'll say a few words. How much do I have nearby? Okay. So I'll tell you something about numerical activity at AEI. So over the last 10 years, Ed Seidel was leading the group here and has, together with a number of people, produced Cactus, which is a generic 3D parallel computational toolkit. It's really meant to solve PDEs, but in particular Einstein's equations. My arrival has coincided with the use inside the group, but well, actually even earlier the group was using this. As part of even developed this together with people in CISA, Whiskey. Whiskey is a 3D parallel code for solution of the relativistic hydrodynamics and magnetodynamics equation. So essentially, these two codes together provide you the whole set of Einstein's equations that you need to solve to study social gravitational waves. We like to think of this as our relativistic astrophysics laboratory. If you are a relativist and you want to do prediction, the only way you can do this prediction of relativistically, astrophysically realistic sources is to build your own laboratory. And that's what we like to think about, how we like to think about these codes. So these are made to study the dynamics of matter and the generation of gravitational waves in highly curved and dynamical spacetimes. Here are some highlights about what we can do right now at AEI. So we carried out a binary black hole evolution for several, in this case, more than 5 orbits. And this is the kind of trajectory now you're seeing people are able to do. I don't think I've seen as many orbits elsewhere, but I'm sure other people can do this. You can start, once you look at this and you recover from the dizziness of looking at this spiral, you realize that there are some interesting features. Most interestingly, you see that there is a certain eccentricity which is rapidly reduced. This is the fact that our initial data are not perfect. They're supposed to be on circular orbits, but they're not. A certain eccentricity is present, and this is removed through the emission of gravitational waves. Then you can, of course, you want to ask, well, what about the waveforms? So this is the waveform. There are 5 orbits, so you can see 10 peaks here. Okay. This part, if I had given this talk 12 months ago, I would have said, so in principle, there is a region where you can do post-Newtonian expansion. Then there is another region, which is this one, where you can do quasi-normal mode fitting of the single black hole produced. And in the middle, there is something which we don't know, and we have to calculate, and we have problems calculating. Well, as you can see, now I have a different attitude. I can show you the whole waveform, and we can fit this part with a post-Newtonian expansion, and we can fit this part with the quasi-normal mode decay of a single black hole. So this is a proof that the field has really taken huge steps in 12 months. Yes? Sorry. Yeah. So we've not been systematic. We just done a visual fit with a 2.5 post-Newtonian template, and we see that we can follow between 4 and 5 peaks pretty well, and then the thing get out of phase. This is in no way systematic investigation on how to do this in the best way. But there is more than vacuum in life, and so we're also doing things with matter. Right now, we're looking at neutron star oscillations, both linear and nonlinear, both magnetized and not. This is an example of a star which is undergoing nonlinear expansions. We've been recently completed a study on the bar mode instability. I think this paper is out today on the archive. We're looking at binary neutron stars, right now we are smashing them. We're looking at binary system in which you have a black hole and a neutron star of comparable masses. This is a very interesting problem if you want to study the emission of gravitational waves and understanding what are the properties. And of course, there is the rotating collapse to black hole, which is something that personally I've spent the last 2 years working on. And I would say something more about it so that you also get a minimum of science besides propaganda. Okay. So if you think about this, collapse is a very common process in nature. Okay, if you just look at the sky and you see that things either expand or collapse, and when they collapse, at the end they will produce black holes, unless they're very small. So this is a classical problem in relativity. The first gravitational waveforms, the first calculations were done in '67 by May and White, but then these were in spherical symmetry. Stark and Piran, in almost 20 years later, were calculating the waveforms. This is done with polar coordinates, and they were able to do this by using non-uniform polar coordinates. They were able to put other boundaries far away and detect waves. This is a very difficult problem. Besides the fact that you want to follow the motion of matter up to a point where everything is concentrated into a single grid point, also from a gravitational radiation point of view, this is very challenging. The efficiency, so the amount of energy you get per unit mass, is very small, 10 to the minus 6, 10 to the minus 7. You look at binary black holes, then you have 4 orders of magnitude more efficiency there. So it's really difficult, given the precision of our codes, which is of the order 10 to the minus 3, 10 to the minus 4, to get such a small signal. And of course, we've done our best to get it. So what we've done is that we started from some uniformly rotating models, either which are slowly rotating, like this object here, D1, or D4. Here you have a way of placing your initial data on this diagram. Here is the mass, here is the central density. Different curves correspond to different rotation speed. The continuous one is a spherically symmetric star, okay, no rotation. And the dashed one is a star which is rotating at the mass shedding limit. It's rotating so fast that if you spin an epsilon more, it will start losing matter at the equator. So we take these two objects and we collapse them. We assume they follow polytropic equation of state. This is the kind of evolution that you see. You have something which starts spherically, then starts to collapse. At one point, we find an apparent horizon, which is this dashed. Let me see if I can highlight this. I can't. You see, there is a long dashed line, and then we fear there is a singularity. So we cut out, as I told you, a Lego sphere. So this is the Lego sphere. You see that between we don't solve inside the Lego sphere, but we solve the equations between the apparent horizon and the Lego sphere. Then you can think about what happens for a rapidly rotating model, and this is what happens. You start with something which is already flattened. It is a spheroid at this point. It flattens like a pancake first on the equator. This is not in equilibrium. This disk is not in equilibrium, so at the end it's actually accreted completely. In this case, what you really want to bear in mind is that if you have rotation, you don't have an homologous collapse. Things deviate significantly from a spherical shape. This is a diagram I love. This is the space-time diagram. If you remember, I showed you at the beginning an example of slicing conditions. Well, that was just a sketch. This is a real calculation. You can see this is for the slowly rotating model. This is the surface of the star. This is a proper equatorial circumference. The thing just goes in. And then there are 4 lines here. Although your eye cannot tell you there are 4 lines, there are 4 lines. 2 represent the event horizon, which starts from 0 size and grows to its asymptotic state. And then there is the apparent horizon, which is instead grows from a non-zero size and is found instantaneously. The reason why there are 4 lines is because this object is slowly rotating. So if you measure its circumference on the pole and on the equator, you get 2 different numbers. And they are so similar that you don't see them by eye. This is the same for the rapidly rotating case. You see that the star starts to collapse. At one point, it actually stalls. As here, you see that the word line is almost vertical. That's when the disk is formed, but it's not in equilibrium, so at the end it actually collapses. And here you can see that the four lines are very clearly distinguishable, and this region here is the excised region, one would cut. The reason why I like this is that each point in this diagram summarizes about 10 to the 11 floating point operation. So this has an amazing summarizing power. Once you read this, you know how to read this, you know how to understand what a simulation like. So in 2005, we had calculated the waveforms from this process. This is an example of how the waveforms looked like at that time. We've shown that the L equal 2 is the dominant mode, and the L equal 4 is about an order of magnitude smaller. This is essentially an axisymmetric space-time. In order to show that these were actually gravitational waves, we've done the following exercise. We don't know. We know they are waves because they can be translated in time, and that's a property of a wave equation. It has to be a function of t minus r. But are these gravitational waves? Well, the only way to tell this is by comparing the waveform frequency with what you expect out of typical frequency of the space-time that you are starting with. So this is the quasi-normal mode of a typical star, or the quasi-normal mode of the black hole. And then you Fourier transform your signal, and that's what you get for the L equal 2. And you can do the same exercise for the L equal 4, and that's what you get. So this is evidence that those waveforms are not just waves, but actually are gravitational waves. More recently, this is a work that I was showing you in the highlights. We decided to challenge the excision paradigm. The reason why we got frustrated with excision is that while at low resolution seemed to be beneficial, at higher resolution it actually turned out to be decreasing the lifetime of our simulation. So we just decided to do without. Of course, in doing this, one has to do a bit of challenge to an assumption, which is the one that what you're doing is the right thing to do. But as I've shown you, that was actually a good assumption. And so by the time we don't do excision anymore, and I'll tell you what exactly we do, we can go well beyond what was possible before and obtain the full waveforms. This collapse produces generic space-time singularities. These are not punctures as the one people use for binary black holes. So this is what we can do. This is the rest mass density. In these lines, the red is what you can do if you have excision. The circle signals the time when an apparent horizon is found. So this is the central density. You see that it increases and then, of course, decreases because after a certain point, the mass is concentrated in such a narrow region that it is dissipated away. But even when it is the central density, I mean, even if when the peak is dissipated, you still conserve mass to very high precision. Look at this. This is the rest mass normalized to the initial one, and just when at the end, when everything is really diffuse, you lose conservation of mass. This is another way of looking at the results. I told you that we calculate the Hamiltonian constraint as a measure of our accuracy. So that's what we do here. We calculate the Hamiltonian constraint inside the apparent horizon and outside the apparent horizon. So this is essentially the dashed curve and the continuous curve. Concentrate on this for the time being. This is the log, and an accurate solution has to have this number as small as possible. And you see that it is outside the apparent horizon, this number is very small, and inside it actually is very large. The way you have to interpret this is that you are not solving Einstein's equation inside the apparent horizon, but you are outside the apparent horizon. And the fact that this curve remains flat is an indication that you reach a stationary solution and that you're not suffering from instabilities. This is instead what happened before. Once the apparent horizon was found, wow, the constraints would blow up and the code would crash. Okay. I will just show you a psychedelic simulation, if I can. So this is the initial wave content which is rapidly removed. This is the mass collapsing, and a point horizon is found, and then you have the emission of those waveforms which I've shown you in the previous slide. You see the quadrupolar nature, and you see now the last burp of the black hole, which is its quasi-normal mode ring, and you see these three peaks. And after that, radiation leaves the grid, and things remain like that without any major problem. Okay, I have to hurry up. Okay, so once you have the whole story, you can calculate what is the energy loss, because you can calculate what are those gauge invariant multiples. You can calculate what is the energy, and you see that we have this kind of, this is the slowly rotating, rapidly rotating. You see, very small. This is much smaller than what Stark and Piran calculated in '85. We know why they were getting such a large number. Essentially, their dynamics wasn't proper. They were using, they were depleting the pressure by large factors, and so they were accelerating and getting larger efficiency. But this is kind of the number people get also from other scenarios, in particular from core collapse simulations, where they also get 10 to the minus 8 or 10 to the minus 9. Signal to noise ratio, you see that slowly rotating stars are hard to be seen even with the advanced detectors, but rapidly rotating ones are likely to be seen with the advanced detectors. Of course, that if for a source at 10 kiloparsecs, so within our galaxy. Now that you know the tricks, how to do this, you can start doing really astrophysics and gravitational wave astronomy. You can study how do the waveforms depend on the perturbation type and amplitude. Sometimes we introduce perturbation to trigger, on the rotation rate, on the velocity distribution, if you have a uniform rotation or you have differential rotation, on the equational state. And these are those steps which are essential to build up our understanding about gravitational wave astronomy and go beyond simple detection. So this is just an example how you can get very different efficiency whether you start. So this is the standard way we trigger the collapse. We just reduce the pressure a little bit by 2%, and you see that these are the efficiency, 10 to the minus 6, 10 to the minus 7 I was reporting. Here I'm putting J over M squared of the initial star. You can increase this by not putting any perturbation, so delta P over P equals 0. You still have this slope, which is delta, which goes like the 4th power J over M squared. Or you can even increase the efficiency by just putting in an initial perturbation in the radial direction. Then you see that these efficiency go up. What happens here, as a matter of fact, is that you're triggering different eigenmodes, and different eigenmodes will have different efficiency while they produce different way in which matter will collapse, and the time variation of the quadrupole moment will be different in the different cases. We are also considering differential rotating stars, and if these differential rotating stars are located about here, so they can be extremely good sources. But overall, what you expect is that you have a signal which is of order, signal to noise ratio which is larger than 1 for a source at 10 kiloparsec, just if you are looking at very rapidly rotating stars. That's the overall conclusion. So I stop here. I think I've already said this a number of times, but let me stress it again. The prospects of numerical TV have never been as exciting as they are now. Several groups in the world are working to investigate the vast space of parameters describing the spiral and a merger of binary black holes. And of course, we are also in this challenge. Some of the simulations which have been recently carried out, both in vacuum and non, have addressed problems that were unsolved for decades. The collapse, one of them. The binary black hole was another, for which people have spent 30 or more years. Our codes, Cactus and Whiskey, have been excellent tools for us to study this problem, and both the binary black hole problem and a variety of matter sources. The bottom line is that I am a deep believer that, as never before, numerical TV can provide physical input in both gravitational wave astronomy and help understanding GR in nonlinear regimes. And I'll conclude with this picture. This is 127 or so people who were here in this campus in July participating to the New Frontiers in Numerical Relativity Conference. And you can see from their faces that they are very excited about what's going on. Thank you.
Questions?
When you said that those are really gravitational waves, what other kind of waves could they have been?
Oh, numerical, for instance.
Yeah, just spurious, so to say.
Yes. So, I mean, this is not a problem for which you have an exact solution you can compare with. Okay.
Yeah.
The best you can do is use all of your understanding of the process, and that's why we use the input coming from perturbative analysis, where people know what are the eigenfrequencies of a black hole or of a neutron star, and just make sure that we're getting the right number.
Mm-hmm. Okay, then a second question. To what extent have your codes developed here have been influenced by this first paper from 1 year ago? You have described that was so important.
So the first paper by Pretorius,
yeah.
Has been influential mostly in showing us that it is possible. It has provided us the optimism that the problem is not without solution, and that there is a light at the end of the tunnel. But right now we are trying to build a code which does the solution in the way that Pretorius does it. Okay, so Pretorius has influenced us in the sense that we are now using a code, building a code which does things as he does. Okay, so we have two codes now, one which does the things in the standard way, and one which does the things in his way. Well, in his way means really a way that other people have suggested, with using this generalized harmonic formulation of the equation. But I would say the other way around. Those results that have been coming up, many of those, in a way have been produced or generated in the first instance right here. The UTB, the group, has spent several years here at AEI and has helped develop a code which is then the one they use there. Parts of the code they've used are shared with us. Same for the NASA group. The people who are at the NASA group have spent long years here. So there has been a kind of diffusion of knowledge coming from the AEI over to these other groups. And so it has been interesting to see that this has actually played a role. And this also helps us have a good relation with these people.
Other question?
Thanks. I have a question about this universality that is found in the merger of two black holes. I didn't quite understand what was changed between two simulations. You said that it is found that the end of the mergers is always the same.
Yeah. So how
but
about
what is the difference in the initial conditions? Is it?
Yeah, probably wasn't.
Is that different approximation?
No. It's just different separations. So you have the same masses. You just place them at different distances. Okay. So let's read this together. R1 is the trajectory of a binary system starting the closest possible. So I think they start here, okay? So it does this and then ends up here. This is a single trajectory, okay? So that you can see better a single black hole. Then you start with the same configuration, having the same amount of angular momentum, and you put them at a different location, R3, and you don't see it's green. Let's look at the red one. You start here, and you see that, okay, initially it certainly has a different trajectory, but then by the time it's here, ends up in the same trajectory. And the same for the R4, which is the blue one, starts here, but then at the end ends up in this. And that's why I think of it as a groove. If you think about a groove and a ball spiraling in, at the end it will end up in the same groove. And you see this from the waveforms. So the waveforms here are different waveforms. They start, the portion that you don't see is where they differ, okay? But the portion that you see is where they are the same, and these are essentially related to this very final part.
So is there a way to connect this, well, the measures state, which is the real, well, last few orbits, to the situation at a much larger distance? I mean, the situation at that we can, well, get from astrophysical context. I mean, we know we have a binary with this eccentricity and some major axes.
So, this universality may be just a universality for this type of initial data, which I think is a particularly symmetric one. You have zero spin, and you have equal masses. It is very likely that if you remove these two assumptions of equal mass and equal spin, you don't end up with the same universality. You disagree? Okay.
There have been people who have argued, is it working? Yes, there have been people who have argued over it, that you can understand the universality by recognizing that while the initial conditions might have, depending upon how you count them, say 14 degrees of freedom in them, the end state has but 4, mass and 3 components of spin. So all of the information that would distinguish any initial data that leads to the same final black hole has to be effaced. It has to be lost.
Indeed, but the point is, where is it that you have a universality? I'm sure that you can have universality from this point onwards. I think we're not debating that. So universality is, do I start counting from here, or from here, or from here, or from here? So,
but that's the entire point, is that as you get closer and closer to the place where you have, just to pick a point, where the true horizon forms, as you get closer and closer, the distinction has to vanish, and it's got to be gone.
Okay, but at that point is obvious. I think we don't disagree. Universality at that point is obviously there. So my point is whether you can really say that the last 2 or 3 or maybe more parts, final, peaks of the waveform are the same, independent of what are the initial conditions. That is something that I don't believe is going to happen. I agree with you that certainly there's going to be a point where all of had to be lost is lost, and so you end up with a rather simple picture. And that's the universal picture one can think of.
I'm not following the distinction that you're making. But
Okay,
that's okay.
The distinction is where you start universality. That's my distinction.
So the last question.
Well, then we agree. So traditionally, particle-based methods have not had a large success in relativity, mostly because it's difficult to write the equations in a covariant form when you have particles. There have been more recent studies on how to do this, and there is some attempt to do this in a way which is consistent. But to my knowledge, there is just 2 groups in the world who use SPH to do this, to do relativistic aerodynamic simulations, and none of them has tried to solve the collapse problem.
So we're going to have a coffee break, and then we'll continue at 11:50.